Thank you for joining back. This was where we stopped. So I was saying that the Gauss elimination method is like very good. It's a standard method we're going to be using. But from the previous example, you know that I told you that the algorithm is that you're going to make this one 0, you make this one 0, and you make this one 0. That's for the elimination. Then you do back substitution. But in this case, you are giving this question, right? And there is no x1, meaning that there's no a1 one time, meaning that the a1 one time is 0. So the first step you're supposed to do is that you multiply this first equation by the coefficient that is here and the coefficient that is here. So since there is no coefficient here, is 0. And if you do this using your calculator, or even if you use a computer program, you are going to get an error message, division by 0. So how are you going to do it? So that's one of the pitfalls of the Gauss elimination. So we are still going to talk about that later, how to solve it, how to go about it if you are given this kind of question, what to do. So the second pitfall is round off errors. So like somebody was actually saying that how many decimal places you are going to use. So round off errors will occur if, for instance, given this question now, if to say I've just used one decimal place, So here I'm just going to be getting 7.0, then 0.3. Then all my answers were going to be in one decimal places. Remember, for the Gauss elimination method, we are doing a lot of computation. So remember that if we use less significant figures or less decimal places, our answers are going to be less accurate. And remember that we are doing a lot of calculation. So we got this, then we also did this calculation, and then we did another calculation where we added. So you are supposed to even do this calculation. So that means that if you use less decimal places or less significant figures, the errors you are going to get is going to keep propagating down and down and down. For instance, now, if I'm to solve for this 0.1 divided by 3, and I converted the answer to just one decimal place, the answers I'm going to get here is going to be, there's going to be errors in the answers because I've rounded off to one decimal place. There's going to be error here in this equation, and there's going to be errors also in this equation because I've not used, so this equation and this equation is going to have errors because I'm not using lots of decimal places. Then when you're doing the back substitution too, the error will keep propagating and the error will keep multiplying because this already has some errors, and you are doing another calculation again on something that has an error. So this one is going to, the answer is going to largely deviate from the original answer. And if you do this computation, you are also worsening it because there's going to be deviation from the original answer because the errors will keep on propagating and it will keep on increasing as the number of computations increase. So that's the round off errors. So as you would in such situation, can't we make an equation 1 become 3 so that equation, okay, yes. Okay, that's a very good suggestion. So Jamil is suggesting that for this division by 0, for this one, I was asking that how do we go about it? So he already answered. So his solution, which is the correct solution, is that this is our equation 1, this is our equation 2, and this is our equation 3. So if you encounter something like this, he already answered that you're going to interchange. So you're going to make you can just interchange. You know, before, this is the equation 1, this is equation 2, and this is equation 3. So in order to mitigate against this division by zero error, what you are going to do is that you are going to interchange the first and the second one. So if you do that, then you can go ahead with the Gauss elimination method. So thank you for that. So I was about to say that, but I first wanted to talk about the other pitfalls before providing the solution. So thank you for that. Thank you for that. So the third pitfall I was talking about is the round off errors. So round off errors, like I was saying, because we are doing lots of computation, we are eliminating, we are substituting, and we are doing it multiple times. And the error is going to, okay, John is asking, doesn't that create an error? No, it won't create an error if you do that. I will go back to that later. It won't create an error if you interchange this and this. It's still the same question. But all you are just doing is that this was equation 1 before. So you are just saying that let this become your equation 1, and yet let this become your equation 2, and this is your equation 3. You are not changing the question. It's still the same question. It's just that you are rearranging. It's called rearrangement, and it's not going to give you an error. So let me the round of errors. So for the round of errors, I was saying, because we are doing a lot of computation, we are doing like we did this computation 1. So this is the first computation we did. Then we did this computation 2, 3, 4, 5, 6, then 7, 8, 8, then 9. We did up to like 10 computation. So if the decimal places are not right, the error is going to keep on increasing. If the round off error is going to keep on increasing when you as at the time you get to your final step. So that's one of the pitfalls of round off errors. So like you would know, the solution to this one is just to increase your decimal places or to increase your significant figures. Then unstable systems, stable systems are systems that for a small change in input is going to give you a small change in output. So that's bounded input, bounded output stability. But unstable systems are just a slight change in the input, then the output is going to be very, very outrageous. That's an unstable system. So we've done stability in digital control. So these unstable systems, it follows from the round off error. For instance, if your question, like if the system is this three sets of equations, if they are unstable, and you know that, and you are using like few numbers of decimal places to do it, you know that I was telling you that if you use few decimal places, the error will keep on propagating, and your final answer is going to be like, it's going to be different, but it's going to be close to the original answer, but it's going to be slightly different because of the error propagation. But if these systems were unstable, unstable systems mean that a small change in the input will give an outrageous output. So if the system was unstable, the result you are going to get at the end of the day is not even going to be close to the original solution. It's going to be very, very far. It will deviate significantly from the original solution. That is if it's unstable. So that's one of uh, the merits. How are you going to do that? And it follows from the round of errors. Then singular systems are systems that they is when two equations are very identical. For instance, given this question, uh, if to say this was the question, so let me just give another question. So if to say the third equation 1.101, then plus 7 point, or let me say plus 6.999, then minus 0.299, then minus 19.301. So if this was the question, this equation is singular. These sets of equations are singular. And the reason why they are singular is because this equation 2 and this equation 3, they are identical. Like, difference between this and this is just 0.01. Difference between this and this is 0.001. Difference between this and this is 0.001. Difference between this and this is 0.001. So these two equations, they are identical. And in such cases, if two equations are identical, that means they are almost identical. That means that they are the same thing. And you are losing 1 degree of freedom. So because these two equations are the same, almost the same thing, you just have two equations to work with. And remember, you want to get 3 unknowns using 2 equations, which is not possible. So those are the pitfalls of the Gauss elimination method. So how do we improve the solution? So like I said, for the round-off errors and for the unstable systems, the simplest strategy is just to use more significant figures and use more decimal places, because then the error propagation is going to be minimal. And if the system is unstable, you know that it's not really going to affect an unstable system. Then the second solution is pivoting. So that was the answer Jami was saying. So pivoting simply means that, okay, so this was the original question. And there's going to be a problem here. Either you are using a computer to do it or a calculator to do it. So the solution is pivoting. The solution he proposed was pivoting. So this is equation 1, this is equation 2, equation 3. So what you are just saying is that instead of, you can make this one equation 1, or you can even make this one equation 1, then you just interchange the equation number. So if we do it this way, then we've pivoted. So what if you pivot? So that strategy is pivoting. So if you do pivoting, you will no longer have the error. You no longer have that. You no longer have that problem again if you do pivoting, because if we wanted to, this is our new rearrangement. So we are just simply rearranging it. So this is our new rearrangement. So in order to use Gaussian elimination, we need to eliminate this one, x1 term. So x1 term is already eliminated. So we need to eliminate this, and after that, we eliminate this. So you just use to eliminate this one. What you are going to do is that you multiply the first equation. You multiply the first equation. So let me just do it. Multiply this first equation by this. So by 4 divided by 2 divided by 4, then the product of the multiplication, you're going to subtract it from the equation you are trying to eliminate, which is the third equation. So you're going to subtract it. So when we do that, we are no longer having division by 0 anymore. So that's the strategy to go. So it's called pivoting. So just interchange. If equation 1 is giving you problem, just rearrange it and use the second equation as the first equation, then you are good to go. Then the third technique is scaling. So scaling is like, so we've talked about pivoting. So scaling is, okay, for instance, let me just present a problem for you. For instance, if you are given this set of equations to solve, and you, if you solve it normally this way, you're going to be getting some errors. And I didn't solve it, but you can just try to solve it on your own. And the reason is that, look at the coefficients. You have 2 here, you have 1 here, you have 1 here, you have 2 here. Then this is like 1 million. 1 million. The coefficients are like, they don't balance out. This is very, very small or negligible. And this is, say, this is 100,000 and this is 100,000. So the way you're going to get errors. So I just encourage you to solve it. You get some errors because of these outrageous coefficients here. So the way to solve it is scaling. So if you notice that one equation is very, very, the coefficients are very, very large compared to the second equation, then you scale that first equation by some factor. In this case, we scaled it by 1,000. So we divided this first equation by 1,000, and so the second equation is okay. So you don't need to do anything. So if you do this, it's going to be better. The errors you are going to get for x1 and x2, you're going to be more closer to your original answer if you do this. So if your questions are very, very outrageous, you can just divide the equation by a constant value, so that it's going to try to reduce the error. Then you solve it that way. So if you solve it this way, it's going to be, the errors you're going to get from this is going to be less compared to the errors you will get when solving it this way. Then another thing is that if you notice these two equations, there's a problem actually, and that problem arises from this. Like, this number is 0. Because we've scaled it, is 0.00002, and is very close to 0. Is very close to 0. So the situation I pointed out in this equation, so let me just put in the original equation. The situation I pointed out with this equation A, with this set of equation, is that, like, if you, for this one here, for this equation here, the x1 is 0. So x1 is 0. So there's a problem here. So this division by 0, it's also occurs. It's not only when your first equation, the first term of your first equation is 0. It also occurs if this number is very, very small. Like, if it's very, very small, it's close to 0. So they are going to be, is not going to give you an error, but then it's not going to, because 4 divided by 0 is going to give you an error. You can't even solve it. But if you do this, it's not going to give you an error. But as a result of this, you are dividing is this, your denominator is very, very small compared to the numerator. So this calculation is going to give you a very, very large number. And when you do the subtraction, these numbers are very small, but the result of this calculation is very, very large. So it's going to give you an error. Like, there's going to be a lot of round-off errors as a result of that. So this situation where you don't have a coefficient here, and you have a very, very small coefficient for your pivot equation. The first equation is called the pivot equation. If the pivot element is very, very small, it's going to result in an error. So for this, we are saying that because of these numbers are very, very large, you can just divide by 100,000 to get a new equation. But then we are having another problem again, because this number is very small, it's very close to zero. So you would have guessed it. So in order to go about it, you'd interchange. You make, this one was your first equation before, and this was your and this is your second equation. So in order to mitigate about this problem, you just make the second equation your first equation, then the first equation your second equation. Then if you solve this using this, then you're going to have less errors. So the what I've just described is very important. So if you are giving in the exam, if you are giving, probably you are giving an equation like this in the exam, and you are asked to solve it using Gauss elimination method, don't just go ahead and solve it like that. First look at some things. For instance, you might be giving this kind of question where there is not even a term here. So if you just solve it without even looking at it, then obviously you are doing the wrong thing. Then also, if your first term is like, so the pivot coefficient is very, very small, you should interchange. So the summary of it is that if you are given a question, don't just, for Gauss elimination, don't just start solving it directly. Just look at it and try to do the adjustments, because if you don't do the adjustment, then obviously you failed the question. So you're going to look at the third method, which is Gauss-Jordan method. So the Gauss-Jordan method is quite similar to the Gauss elimination method. The difference is that for the Gauss elimination method, let me just explain it again. You have this A coefficient. So you want to you zero out this, you zero out this, you zero out this. Effectively, you are converting this matrix into a upper triangular matrix. But for Gauss-Jordan method, you are converting the matrix into an identity matrix. So you have this matrix here, and for Gauss-Jordan, you want to convert it into an identity matrix. So the first step is that you want to turn this 1 to 1, this A11, you want to make it to become 1. Then after that, you zero out this, and you zero out this. Here's 0, and here's 0. Then the next step is to make this one to become 1. Then after doing that, you will zero out this 0. Then you zero out this coefficient, you make it 0. Then the last stage is that you will make this to be 1. Then after that, you will zero out this, become 0. Then you zero out A23 to become 0. So that's the procedure for the Gauss-Jordan method. So we're going to use the same example, but now we're going to use the Gauss-Jordan method. So for the Gauss-Jordan method, you're going to convert the question in matrix form. So you have a 3x4 matrix. So where you just put in the coefficients, all the coefficients in the question in matrix form. Then the first step is that you want to make this one to become 1. Then how do you make this to become 1? You just divide by 3. So you just divide the first row, each element in the first row, by 3. So when you divide it by 3, you've made this to become 1. Then the next step is to make this to become 0. To make this to become 0, and to make this to become 0. So how are you going to do that? In order to make this one to become 0, you're going to multiply the first row by 0.1, because this 0.1 you want to become 0. So you multiply the first row by 0.1. Then the result of the multiplication, you subtract the second row from it. So this is the second row here. So you multiply 0.1 times the first row. Then if you do this arithmetic, you're going to effectively zero out this one. So you arrive at this this new second row. Then the next thing is to zero out this 0.3. So you're going to use the same strategy. Since it's this 0.3 want to zero out, you multiply the first equation by 0.3. Then the result of it, you're going to subtract from the third row. So when you subtract this from this is going to turn to 0. This one is going to turn to 0. So we are moving forward. Here is 1, 0, 0. The next step is to convert this to 1. We want to convert this to 1. So what you just do is that you divide the second row by this coefficient. And once you divide it by this coefficient, you've converted it to 1. So it's going to cut across each of all the elements of the row. Then after doing that, we want to make this to be 0. We want to convert this to 0. I want to convert this to 0. So we use the same strategy. Since we want to turn this to 0, we are going to multiply this coefficient by the first row. So this coefficient by the first row. Then the result of it, we are going to subtract from the so we're going to multiply. We want to zero out this. So we're going to multiply this coefficient by the second row. By the second row, not by the first row, by the second row. Then the result of that, we'll subtract it from the first row. Since it's the first row, we want to zero out. But you're going to use the second row to achieve that. So if you do that, this is going to become 0. This is going to become 0. And you've zeroed out this one. So in order to zero out this, you multiply this coefficient that is highlighted by the second row. Then the result of the multiplication, you subtract it from the third row because it's the third row you want to zero out. Then if you do that, we are going to arrive at this. So you zeroed out this and you zeroed out this. Then the last stage is that we want to make this to become 1. So remember what we are turning it into an identity matrix. So for an identity matrix, 1, 1, 1. So the diagonals are 1, then the remaining elements are zeros. So we want to make this one to become 1. So we just divide all the elements in this row by this coefficient. And when we do that, here is now 1. Then after that, we want to zero out this. I want to zero out this. But this is okay. We're not zeroing it out. So in order to do that, we'll multiply this coefficient by the third row because we're not zeroing out the third row. So we just multiply it by the third row, which is this. Then the result, we're going to subtract it from the first row. Since it's the first row, we want to zero out. So if we do that, you zero out this. Then to zero out this one, like you would have guessed, we'll multiply this coefficient by the third row because the third row is okay. We're not using the third row. Then the result of that, you subtract it from the second row. Since it's the second row, we are zeroing out. Then we arrive at this. So we are done. After this step, we've converted the matrix into identity. So there's 1 here, there's 1 here, there's 1 here, and the remaining is 0. So we are ready. When you've gotten to this step, you've gotten to your final answer. So x1 is 3, x2 is minus 2.5, and x1 is 3, x2 is minus 2.5, then x3 is 7. So this is the Gauss-Jordan method. So you should note that the pitfalls or the downsides of the Gauss elimination method is the same thing with the Gauss-Jordan method also. So if you are given an absorbed question and you are asked to use the Gauss-Jordan method, first don't just start calculating immediately. You first of all look at it and see the adjustments or the rearrangements you have to make before eventually using the Gauss-Jordan or the Gauss elimination method. So this is the end of the class for today. We are solving, we've moved to another topic, which is solving linear sets of equations. So the topic is actually um, solving linear sets of equations. So we are in the first part. So next week we're going to do part 2. So part 2 is LU decomposition. So we're going to use LU decomposition to solve it, to solve linear equations. Then the last part 3, is we're going to consider software packages that we can use to solve linear equations. So you can majorly MATLAB and Excel. Excel will be which we have been using throughout this course. So thank you very much for joining.